Hi, everyone. Welcome to another Priberam Machine Learning Lunch Seminar. Today we have with us José Pombal. He's a senior researcher in Sword Health and also a PhD student here at IST. Today he's going to talk about quite an interesting framework for creating zero-shot benchmarks. Take it away.
All right, thank you. Hello, everyone. It's a pleasure to be here. Thank you for the invitation. I'll be talking about zero-shot benchmarking. It's a framework for, as the title says, flexible and scalable automatic evaluation of language models. This was work done with Nuno Guerreiro, Ricardo Rey, and André Martins at Unbabel. And if I'm gonna be keeping track of time, because if I would like also to perhaps talk a bit about some follow-up work that we've done inspired by this work since in sword health and mental health applications. So hopefully I'll talk a bit about that as well. All right, so to start with a bit of motivation, obviously for anyone working in the field, you know that benchmarking is essential for scientific progress. It's how we measure whether any experiment we do works or not, and language models are no different. Everyone uses benchmarks or evals, as they've now been called. And but traditionally, it tends to be a slow and complex process. Obviously, I mean, we want to make sure that these benchmarks are correct and that they measure meaningful things. And because of that, we also put a lot of effort in them. But this slowness and complexity is becoming incompatible with the speed at which technology moves in the language modeling field with large language models, and with this paradigm of every 3 months something becomes obsolete. But to give you a bit of context, obviously, usually how a benchmark is created is you have a certain task, let's say translation, and we usually reach out to human experts and ask them to create a set of interesting instances to evaluate model performance. So for translation, that would be sources like just sentences, documents, what have you in certain languages. For question answering, it would be questions about any topic. Then you'd get model responses over those instances, and you'd also do some evaluation with human experts. So this is kind of the ideal case. And if you want to get a really good notion of whether your model works or not, you do this. So all humans through and through, you have human experts evaluate the responses that your model gives. Now, this is great, but it has a problem. It's very slow and expensive. I have this $100,000 figure there. That's for the creation of GPQA. Some of you might know it. It's a multiple choice question benchmark for PhD level physics and chemistry questions. The evaluation is actually not manual because it's multiple choice, so it's just accuracy. But it costs $100,000 to create. And one problem, and this is something that really marked me in my PhD journey. 2 years ago at Column 2024, GPQA was accepted as a spotlight. And the beginning of the presentation was, the main author said, we did this benchmark, it's great, but we did it 6 months ago and it's already saturated. So models can already sort of max out its performance, or you can't really use it to distinguish a good model from a bad model. And all of that cost $100,000. So a lot of effort. It's a nice benchmark, but it has this problem, this paradigm. Benchmarks are hard to update. So they become saturated quickly, especially now. And perhaps even worse, they are gameable. So models are quick to also with the whole community optimizing and doing, training interventions to become better at a benchmark, the benchmark stops being useful to really tell apart model quality. And it's also very difficult because of this cost. It's difficult to build good benchmarks for niche tasks where there might not be so much interest or so much availability of human experts. So as model capabilities improve, and this sort of scalability problem becomes more and more of an issue. And you can partially solve it by automating the left part, the right part, the automatic evaluation part, instead of using human experts. Let me just make this smaller. You can have some sort of automatic metric, as you have, if some of you are familiar with translation, you have these metrics like Comet, metric X, that are trained to be evaluators. So you sort of take out the human component of that part. But it's still, this part of data creation is still a very big bottleneck. And it doesn't really solve the other issues of the benchmark being hard to update, and so gameable and not very useful as models improve. So a direct idea, and sort of the main idea we had with this project was, why not automate both? So we already do automatic evaluation. Why not also automate data creation? So ZSV is really about automating the entire benchmarking pipeline. So not just evaluation, it's also about creating data automatically to serve as sort of evaluation test, as an evaluation test bed for models. And this, I mean, it's a pretty simple idea, but it's quite promising, because if you automate everything, everything becomes much faster and cheaper. And more versatile, potentially, as well, because it is faster and cheaper. But the question remains, I mean, are these benchmarks any good? Are these benchmarks useful? And that's sort of what we set out to, that's what we propose, and it's what we set out to show in this work. So the framework of zero-shot benchmarking is about automating those two stages of benchmarking, okay? So data creation and evaluation. And so it requires, you essentially require at least a language model. You can think of GPT, Claude, Qwen, what have you. And you have to do at least 2 prompts. And this is the simplest instantiation of the framework, okay? You can think of anything that's more complex. You can think of using several language models, not just a prompt, like an entire harness. That's up to your imagination and the complexity your task requires. But in its simplest form, and that's what we're going to focus on, you just need 1 model and 2 prompts. So the first prompt is the data generation meta prompt, where you describe the task you want to create data for. And for example, here is an example of a prompt. You don't need to read that, but it's you essentially have a description. We want to create a sort of a chatbot arena-like benchmark to evaluate general capabilities like knowledge and instruction following. And then we have in the prompt these placeholders for like language and topic, subtopic, difficulty, and writing style to generate instances with different, varied instances, obviously. Then this, you can also use other inputs. Like I said, this, just using the prompt is the simplest version of this. But if there's pre-existing data like images, you can put that in the prompt as well. If you're creating a benchmark for vision language models, you can use any other form of pre-existing data, like corpuses that you might have. You can ask for a reference, anything. But in the simplest form, it's just a prompt. And then this yields a series of test instances. These may be questions or texts to be translated, anything you might think of. You get model answers, as usual. And then the second part that you need to do is the judgment prompt, okay? So this is where the rest of the human effort goes into, is designing the judgment prompt that is also passed to a language model. So you might be familiar with this term of LLM as a judge. Everyone does this now, where you just prompt the language model to evaluate. And in this example, we have a Likert scale from 1 to 6. Based on a few criteria, we're asking the language model to rate each instance from 1 to 6 based on some criteria. But again, this prompt can be anything. It doesn't need to be a Likert scale. It can be like, you can ask the language model to choose the best out of 2 answers. You can give the language model like a checklist with rubrics and ask the model to say which rubrics are fulfilled and which are not. Up to you again. But a Likert scale is a pretty common and popular format. And you pass this to the language model, and you obtain scores, in this case, for each instance of that you created. And then to get some sort of final score for the model, you can aggregate those scores. So it's quite simple, okay? Just have 2 prompts and use a language model. So it's turtles all the way down. And so this makes ZSV very scalable. I mean, everything's fully automatic, so no problem there. It's versatile. You can potentially apply it to any task. Just change the prompt, adapt the prompt. You might need a sufficiently strong language model. Maybe if you take Llama 2 7B from 3 years ago, which is like prehistory, that this won't work, but maybe if you use Claude, it will. And perhaps most importantly, I think it's updatable. So because it's scalable, let's say you create a benchmark like this. Then you use it for a while, a couple of weeks, or maybe a couple of months. But then models improve in your task, and you do some sort of model training, and you become too good for the benchmark. No problem. Create a more difficult benchmark. Learn from what your model can already do and what it cannot do. Adapt the prompts and create a new benchmark. So this idea is very focused on model development. Okay, like you're not going to use this maybe to say that your model is the best in the world at something, but it's definitely potentially useful for developing models at a fast pace where you can constantly update benchmarks. And I think that the important lesson here is that traditionally, the usefulness of a benchmark is negatively correlated with the quality of language models. So as language models improve, the benchmark becomes less useful because you can't refresh it easily. It's a human-created benchmark, so models just saturate it. With ZSV, and by automating everything and relying on language models to create benchmarks, the usefulness of the framework actually correlates positively with the improvement of technology. I have this anecdotal experience in practice where certain things that we wanted to create benchmarks for were not possible 2 years ago and are now possible with better models. And we are able to solve new tasks just by doing this sort of process of, okay, let's use the better models now and use them to create a benchmark now. And we're able to measure performance in things that we weren't before. And there's also kind of a perhaps deeper philosophical question here where you might ask, okay, what if I have the best model in the world? Like, and I want to evaluate its performance on a certain task. How can I, if I'm using some language model as a judge, how can I use a weaker model to evaluate the performance of a stronger model? For two reasons. First, how can I create data instances that I cannot solve? And two, how can I evaluate things that I cannot solve myself with the weaker language model? And for the first, I have anecdotal and empirical evidence for this in the work as well, but there's also sort of two arguments for this. First, there's a ton of problems that we can think of. I mean, just think of all the unsolved maths problems that are out there. There's a ton of problems that we can think of that we cannot solve, but someone else can. And the second thing is, I'm sure, I hope none of you here are a professional translator, or perhaps some are, but you would be hard-pressed to translate a Saramago novel into English very well. But I mean, it's a very hard task. But if I showed you a good translation of Saramago in English and a bad one, you'd probably be able to tell them apart without any background in translation. So there's no need, and empirically we see this all over the place. There's no need to have a perfect model to create challenging benchmarks and to be able to discriminate between good answers and bad answers. So hopefully these arguments will have convinced you slightly on why this makes sense to automate everything and why these benchmarks can be very updatable. On the other hand, I'd also like to tell you what ZSV is not. So ZSV is not just LLM as a judge. So like I said, we use LLM as a judge as one component that's sort of automating the evaluation part. But we also propose automating the data creation part. It's also not a replacement for humans. It's mostly, I think, and for us in practice, we use it a lot for model development. But at the end of the day, if you want to, do something like WMT, which is a competition for machine translation, if you want to state every year which is the state-of-the-art model for translation, you probably want to do some sort of expert evaluation. Same thing for safety audits and evaluations. If you deploy a model in the real world, you want to go through humans as well. And it's not static, so it's not just one benchmark. Okay, it's a framework for creating benchmarks. So I'm going to be talking a lot in the results part of this presentation about benchmarks we created, but the framework itself can be used to create new benchmarks at any point. So all of this sounds very good, but does it work? Like, do benchmarks created like this, are they predictive of model quality? Are they useful to tell good models apart from bad ones? So the rest of the paper we dedicate to meta-evaluating ZSP, so sort of evaluating the evaluation method. And the metric we use is system pairwise accuracy, where essentially the way we measure whether a benchmark is good is by taking a bunch of systems, a bunch of large language models, and checking some human rankings for that task. So let's say, for example, in translation, we have human rankings for many systems. And we say that a benchmark is good when the rankings that the benchmark predicts are similar to the rankings given to us by humans, okay? And we measure this with pairwise accuracy, which is a form of Kendall-Tau correlation. So it's just a ranking correlation. In practice, what you do, let's say you have a human ranking like this for a task. It's Qwen, Claude, GPT, Llama. And you have a predicted ranking by a benchmark. So Claude, GPT, Qwen, and Llama. What you do to calculate pairwise accuracy is you take every possible pair of models. So Qwen, Claude, Qwen, GPT, Qwen, Llama, and so on and so forth. And you check whether the predicted ranking in the benchmark is the same as the human ranking. And if it is, okay, you count one, that's one for the metric. If it's not, that's a 0. And then you do the average of that, and you get a value between 0 and 1. The bigger, the better. In this case, benchmark 1, for example, you see right away, Qwen and Claude are not ranked properly by benchmark 1. So there's a loss there. On the other hand, GPT and Llama are ranked properly, etc. You come up with this figure of 0.66 pairwise accuracy. But if you take benchmark 2, which has this ranking, if you do this math, sort of comparing all pairs of models, you come up with this figure is 0.83. And this is what our metric to say that benchmark 2 is better, okay? Because it predicts system rankings better than other benchmarks, which is another way of saying, if I found 2 models in the wild, this benchmark would be better to tell me which model is better than benchmark 1, which is essentially kind of the main challenge in model development, where you're trying many things. You know, you're trying to train your model in many ways, and you want to understand which one works better. That's essentially the basis of how you do this. So this is our metric to tell if a benchmark is better than another. And then we want to show that CSV works across a diverse set of tasks, languages, and modalities. But we also need human ranking, so we can't just do, like 1,000 tasks, because turns out that there's not a lot of human rankings of LLMs for a lot of things, because again, it's something that's not super easy to obtain. So the tasks we focus on are first multilingual LLM general capabilities. This general capabilities is an umbrella term for a sort of mix of knowledge, chat capabilities, and instruction following in 4 languages. There's human rankings for this by the chatbot arena. If you don't know, it's a sort of a platform where people generate completions to a prompt and sort of select the best ones. Then we also look at translation across 11 language pairs. That's the language pairs from WMT24, a pretty famous data set, and there's human rankings for that. And then finally, we look at VLM general capabilities, which is essentially it's similar to this data set, but you insert the vision component. So we want to show that, okay, not only can you use ZSV for a few different tasks, you can also switch modalities or add this new modality and it still works. So we're going to be creating benchmarks for all of these things, okay, on the fly. And it's going to cost us in total $5. And by the way, the model we're going to be using is Claude 3.5 Sonnet, so pretty outdated, but yeah. I'm going to skip these slides. These are just examples of the benchmarks we created. Then, what do we want to compare against? Our baselines here are other benchmarks. So ZSV is a framework for creating benchmarks, so we need to beat other benchmarks at ranking models. But we're not going to compare against individual benchmarks, because that's usually not how practitioners use benchmarks. What people usually do is you have what people call a set of standard benchmarks. You might have heard of the Open LLM leaderboard, perhaps, or MMLU, or GPQA, et cetera. What people do is they take a bunch of these different benchmarks, they measure the performance of their system in every benchmark, and then they aggregate the score somehow, okay? to say that my model is better than this other model. If you check out Llama, Quen technical reports, this is also always a big part of their evaluation. And the most naive way to do this aggregation of benchmark scores, to sort of obtain system scores, is averaging benchmark scores. A lot of people do this. It's not super smart, but it is what it is. Then there's a sort of smarter alternative where you take what the border count on these benchmark scores. So instead of averaging the raw scores or some sort of transformation of the scores, you average the rank that a model gets on each benchmark. So this sort of averaging is more robust to outliers and more robust to changes in scales of scores in benchmarks. Because if you just do averaging of scores, your final ranking might be dominated by a couple of benchmarks where some model has a disproportionately high score. That won't happen with border count. So it's a more, I guess it's a smarter baseline. But in conjunction, these two methods essentially summarize how people use standard benchmarks in the wild. Then we also have these two performance upper bounds. I call them upper bounds because they're kind of unfair baselines, unfair against us. One of them is mArena Hard. It's an automatic benchmark based on the same human-created data from which we take human system rankings. So it's kind of unfair in that there's that sort of leakage. And we also take the top one benchmark. So these two baselines are aggregations of benchmarks. What we do also to create this sort of unfair baseline is we look into this pairwise accuracy of each benchmark in the aggregation. We choose the best one to sort of give us an upper bound of the best possible benchmark in that group. This is unfair because you can't do this in practice. You don't have, you don't have human rankings in practice, so you can't like magically know which benchmark is the best. But it gives us a good notion of kind of an upper bound of this aggregation. And so moving to results, we have this main plot here, where we have pairwise accuracy on the y-axis. Okay, so this tells us the higher a bar is, the better a benchmark is at predicting human rankings. So the more useful it is in practice. Then each group of bars, this is for general capabilities. Okay, so each group of bars is a language, and the final group is for vision language models. And then each bar is a benchmark. So the blue bars are ZSV, the benchmark created with ZSV. And the gray bars are baselines. So the light gray is average aggregation, and the dark gray is border count. The line plots are the unfair baselines, kind of the upper bounds. And in 3 of the 5 cases, ZSV has higher pairwise accuracy than standard benchmark. And in the other 2 cases, it has lower than border count. So if you're using border count aggregation, so do use border count aggregation because that works better than average. But the point here is that ZSV is either better, competitive, or slightly worse than human-created benchmarks at predicting human rankings for all these different languages and even in vision in the vision domain. And again, it's remarkably easier to create and to update and to improve. For translation, the story is slightly different because the baselines are also slightly different. This plot, the colors aren't very good, but each bar is also a baseline. But the baselines are even harder than the previous ones because this pairwise accuracy is computed on WMT rankings, which is human rankings based on the WMT test set. And the way we obtain pairwise accuracy with these metrics, these baselines, is we use that same test data. So again, there's this sort of leakage between the baseline test data and the human test data. And then the rankings are obtained with metrics, different metrics. So this is metric XL, metric X, XComet, Comet QE, which are translation-specific automatic metrics. Okay, so these metrics were trained on millions of translations. They were trained to evaluate them. So they had this very deep and very lengthy training process to be good at ranking systems or ranking translations of different qualities. And in any case, ZSV at the far right here with the blue bar again comes quite close in terms of pairwise accuracy. So maybe up to 5 points behind, which is a bit of a gap. It's a measurable gap, but it shows you how far you can get with a very naive approach of just, you have a few prompts, you have a language model that was not specialized at all for this task. Neither did we do any sort of specialization of the test. We just asked the model to create some sources and then ask a judge to judge the quality of the translation. There's no like domain adaptation or anything. And we get quite close to very machine translation specific methods. So I'm always interested by this result. Then we do a series of ablations. I'm not going to go too deep in the results of that, just to let you in on the main findings. We also find that ZSP works well with diverse evaluation rubrics. So not just using that Likert scale that I showed at the beginning, but also doing pairwise evaluation, or even an ELO system like they have in Chatbot Arena, you reach similar results. And it's robust. If you use several different prompts, you can get similar results. So there are better prompts than others, obviously, but the method isn't super sensitive to a very specific prompt or anything. Then we also show that open models are competitive for benchmark creation. So both on data generation and evaluation, you don't need to use Claude 3.5. That's the model we use, but you can get just almost as good results with Qwen 2.57 7TV at the time. That's already a very outdated model. But with the caveat that you can't just use any model for judging, we find that you can only get good quality judgments up from a certain size. And this might not be true nowadays. This was 2 years ago. Maybe with the new generation of open models, possibly, very likely, I think you can get better results. Then we do find that CSV works best when you have the same model family on both stages. So when you have the same model creating data and also evaluating. There seems to be some synergy between these two stages. And we find that the main driver of performance for a given benchmark, so the main driver of pairwise accuracy, is dataset variety, benchmark variety, and not size. So you can get away with reaching that. In our main experiments, we created, each benchmark had 500 instances, but you could reach very similar pairwise accuracy values with just 100 instances, provided that your data generation meta prompt elicits enough variety on the dataset instances. So this is to say that your time is better spent, or your compute, what have you, in creating a better prompt or creating a better system for eliciting this variety in the benchmark than it is spent in just scaling up and creating like 10 million dataset instances for the benchmark. Then, if you might be wondering, what do these dataset instances look like? Like, what are they actually measuring? We had this, this was an experiment suggested to us by reviewer 2. It was actually reviewer 2 in the conference we submitted this work to. And it's a comparison of the topics and the distribution of topics of our English language ZSV for general capabilities versus ArenaHard, which is kind of, at the time, the standard benchmark for this sort of thing. And it turns out, I was quite surprised with this, but it turns out the ArenaHard is half of it. So this is, both of them have 500 instances, okay? So half of it, half of ArenaHard, the gray bar, is code. So they call it general capabilities, but most of it is code. Whereas our benchmark is mostly like instances related to advice and brainstorming, like questions and things that you might think that you want to ask ChatGPT every day. And there's a lot of creative writing and persona elicitation, whereas ArenaHard is mostly code. So this also shows that we were able to reproduce these human rankings with a very different data distribution. So we made no effort at the time. We wanted a fair baseline. We made no effort to try to mimic the data of ArenaHard, which yielded the human rankings. And even still, you can get nice pairwise accuracy. This is to say, though, if you did want a data set that was distributed more like this, so more on the coding side and advice and brainstorming and question answering, you could easily do it. Just go to the prompts and create some prompts that are more focused on or placeholders for the prompts that focus more on these tasks. So it's easy to do as well. So to conclude, on ZSV, we introduced this framework to create benchmarks for LM tasks fully automatically. We show that zero-shot benchmarks can be competitive to or outperform widely used standard benchmarks across 3 tasks and 2 modalities. And we show that the most important factors driving benchmark performance are dataset variety and model size. And we release all prompts, code for creating benchmark. It's all on our GitHub. And this, I just want to, we have a few minutes still, and I'd like to share another work, because this work of zero-shot benchmarking, I think, happened at a time where this part of the field, at least concerned with automatic evaluation of language models, was shifting towards this idea of let's automate everything, let's make very dynamic benchmarks. And we continued this sort of line of work into the work that we're doing at Sword right now with MindEval, which is an automatic benchmark for measuring the quality of large language models in mental health related conversations. So with MindEval, our motivation coming in Sword, this is a more recent work, but you'll see that the idea is very clearly related to ZSV. Obviously, mental health is a very important problem, global problem, and AI can be part of this solution in terms of, perhaps getting to people that can afford mental health care or some sort of stepped care model. But current models, as I'm sure you've noticed, are very sycophantic. They always agree with you. They have a very easy tendency to agree with whatever you say. They don't set adequate boundaries, and they have a tendency also to reinforce whatever beliefs you have, even if these beliefs are bad. This is not very conducive to high quality therapy. And we set out to build better models for this kind of task. But we noticed that there was a dire lack for good evaluation methods. The evaluation methods that existed were pretty much book knowledge sort of question, multiple choice questions, and very shallow question answering benchmarks. Like, I'm feeling anxious, what should I do? Things like that. So it was very simple. And we knew that, if you want to have a model out there actually talking to people about mental health related topics, you want to evaluate that, you need a more realistic benchmark. You need something that more closely emulates the experience of talking to an LLM live. So this is what motivated MindEval. And the idea, I'm going to skip this slide. The main idea with MindEval is we have this clinician large language model that we want to evaluate. Okay, so this is the model whose performance we want to evaluate to see if it's good or not at engaging in these mental health related interactions. And then we have, so to evaluate it, what we do is we make it interact across multiple turns. So not just a question and an answer, multiple turns, just an open-ended interaction with a patient LLM. And this patient LLM is simulated via this patient context, which contains some information of demographics, personality, etc. And this part, okay, so you might already be seeing sort of the ZSV pattern here. So this part, this left part, is kind of a fancier data generation meta prompt. So the meta prompt sort of comes here, and you have this separate language model, and you don't just have like data instances, you actually have dynamic interactions. And then we pass each interaction to a judge LLM, which is tasked with rating each interaction on these 5 criteria, which are related to therapeutic competence. And these criteria were inspired by APA guidelines, and we worked on them with licensed clinical psychologists. And the judge gives a score on each of these criteria, and then you can sort of average these out and average the average of each criteria over any interaction, any number of interactions you want across different patients, and you have sort of your final score. So our idea with this is here to really simulate an actual interaction. So not just a question, not just an answer, an actual interaction that might have ups and downs. And you see that this right part is just the judge part of ZSP. So mind eval directly drinks from the at least conceptually from ZSV, in that we are creating an entire benchmark that we can refresh at any point, that we can improve. We can change the patient LLM. We can improve this context, as we have been, by the way, since mind eval came out. We've done a ton of work in improving this idea, making it more realistic. And we can do that fully automatically to have a more meaningful benchmark for therapy. So I don't have a lot of time, so I'm not going to go over every detail of mind eval. I'm just going to say that we did a lot of work on most of the paper is focused on measuring the realism of the patient LLM. So obviously the quality of this benchmark hinges on whether you can simulate patients in a realistic way, and also whether the scores that the judge model gives you are actually meaningful. So whether it actually predicts scores or rankings that psychologists would give to different models. So on the side, so I'm going to skip this part. On the side of the patient, we have this plot where we generate a series of interactions with simulated patients, and then we ask some psychologists to also simulate patients themselves, so to pretend they are patients with the same profiles. And this is a plot of t-SNE embeddings of each turn in every one of those interactions. So each dot here is a turn, is a piece of text generated either by a human, the blue crosses, these are human generated, or by an LLM. And the orange dots are generated with our prompt and our sort of patient setup. And then the purple dots, purple and yellow, there's a bug in this plot, but purple and yellow is the same. And then green dots are generated with a different version of this prompt. I'm not going to go too deep into this, but the sort of the main finding here is that we managed to sort of get the most coverage of these different prompt setups with our prompt. So we managed to sort of get closer to the human distribution. But we do notice a core flaw, which is you'll notice that there's this cluster over here, for example, is just human turns. And it's actually the most blatant sort of shortcoming of at least this iteration of patient simulation, was that we noticed that patients never refused or very rarely refused suggestions, or patients were not hard. Whereas humans can be, and human patients, these are therapists simulating their experience with human patients, but humans can be much more, they can give you a lot of pushback. So that's one shortcoming we found that we've been trying to fix ever since. And then on the judge side, we have this correlation matrix. To summarize, this is basically, we generated a series of interactions automatically. And we asked a group of 4 psychologists to score the interactions on each of those criteria that I showed at the beginning. And each entry here on this matrix is the correlation between the annotator in the row with the annotator in the column. And P1, P2, P3, P4 are humans. Okay, these are psychologists. And average P is the average of all psychologists. And then mind eval is our judge. Okay. This is Kendall Tau. These two metrics are quite similar, but let's just focus. The findings are the same, so let's just focus on this lower diagonal part of the matrix, where I'm not going to go over each value, but the main point here is that the correlations that we can get with the mind eval judge are on the same level as humans get among themselves. This to say that essentially our judge and the random human psychologist agree as often on interaction scores as psychologists do between each other. And this is not always high. Some correlations, for example, but with P2 seems to be a bit of an outlier. So the values are much lower. But with some, in other instances, 0.42 Kendall is quite high for this sort of thing. So yeah, I'm gonna stop here. I think it's a good point to stop. This is pretty much the main gist of the Mind Eval work, and I'm gonna give you some time for questions, perhaps. Thank you.
So we have time for questions. Do you have any questions in the audience? Yeah, go ahead.
My question is about PFP.
Mhm.
So when you discussed about the baseline for aggregation,
Yeah.
you kind of pointed out the problems with the arithmetic mean.
Yeah.
Of the arithmetic average, right? So you solved that using the border, right?
Yeah. Oh, yeah, more or less. Yeah.
When I was looking at that, I was immediately thinking about geometric.
Mm.
So
Okay.
if you do the geometric average, what would you expect? Would it be closer to border or?
Yeah, that's an interesting question. Frankly, I have no idea. I've never worked. I've never done experiments with geometric mean.
By using border, you're getting more stable.
So the idea would be to sort of kill out outliers, kind of, with the geometric mean. Okay. Yeah. So if that's
One of the models is too fast.
Mhm.
When benchmark,
Yeah.
it will go lower than when you're doing the arithmetic average.
Yeah.
So it kind of promotes things that are more stable.
Yeah. Yeah. I see.
So
So
that's the effect you get with another stuff.
more or less, yeah. No, that's a good point. So I would expect it in that, since that's the motivation, I would expect it to work perhaps slightly better. Although I do have to give a disclaimer. This is actually a better version of average, okay? Because I mean, not in all baselines, we weren't able to do this in all baselines, but for the general capabilities benchmarks, our baseline was the Open LLM leaderboard benchmarks. And what they do there is not just averaging. They standardize each benchmark score by the random baseline of that benchmark, and then they normalize every. Then they do like some sort of additional normalization on top of that, precisely to sort of try to, because let's say, for example, in MMLU, every model has like 90 something, so they sort of scale that down to a common scale that's similar to other benchmarks. But it still has some problems. So yeah. I would expect. I don't. Yeah, I don't think they do in the OpenLM leaderboard, but it could be a good idea. Yeah.
It's now when you generate some. That's why the thing in benchmark, you also apply your
Yeah.
These LLMs might have probably generate and I was wondering that was from how do you generate kind of unexpected values that are mean?
Yeah, that's a great question, and there's actually this whole line of work from this researcher on translation called Willem Zulhar. I got a very similar question from him. He's working on this idea of not all benchmark instances are equally important to discriminate models. So how do we identify more difficult questions, and perhaps even better, how do we generate these more difficult questions? So that's a line of work, and I'll point you to his work on that, at least for translation. To answer that on from the perspective of VFU, we didn't really do experiments on that, but I would say that my best option for that would be to, instead of just using one prompt, to do some sort of iterative process here, where we could use more than one language model, perhaps one prompt specifically tailored to create like hard questions. Perhaps even if you have examples of what it means for a question to be hard in your task, that would be even better. For example, in our mind-eval paradigm, what we noticed, we didn't have this in mind-eval, but something we're working on with to create harder patients. I guess we don't really have a notion of instance in mind-eval, but we have a notion of what is a harder interaction. You can definitely do that, but we found some methods that are not just via like one prompt. You might need to do something that's a bit more fancy, but I think it's definitely possible. I would say that I think that one more conceptual takeaway from ZSV is that I think your time is better spent in figuring out how to describe what it means for an instance to be difficult in your task and to iterate on that instead of actually spending that time in creating difficult instances. So from our experience, if you have a specific enough prompt or a specific enough generation process, you will be able to get there with language models, and that's much more scalable than having humans create the instances themselves.
Actually, it's just a comment. The problem of aggregating rank.
Yeah.
Very general problem, and I think that it can probably do better than border. That in particular, we have to use this ranking aggregation in a number of high relevant voting dynamic positions up, and we use something instant runoff, which is a way to get different rankings and get one ranking that better reflects the aggregation ranking.
Right.
To try this against border count.
Yeah. That's a good comment, and I'd be definitely curious to see like how good that is. I'm willing to admit that will work better. One thing though is whatever aggregation method you use is not mutually exclusive with ZSV, because we can also create like a bunch of different benchmarks and use that to measure standard general capabilities. What we did was like the simplest form, which is just one benchmark. But yeah, that's a good point. I definitely think we could do better in aggregating all these sources of information.
Hi, my question about biases.
Yeah.
So there's a number of different biases.
Right.
Thinking about self.
Yeah.
Did you look at that at all when you're generating the data set itself?
Yeah.
With the model, does it then the models same family score better on that?
Yeah. So we didn't explicitly look into that, although we are very aware, very painfully aware that that's a problem, especially self-preference. I have some recent work on that as well. It's a super interesting topic. Short answer is I did find anecdotally that was a big problem. So I mean, we're using LLM as a judge. That's normal. And for example, in our translation benchmark, we noticed that Claude would consistently rank itself much higher than, I mean, not much higher, but higher than other models. And of course, we can measure this because we have human rankings. But I think we might have maybe a sentence on that in the paper where we say that anything you can think of to alleviate that problem that you would do otherwise, which can be instead of using one judge, use a set of different judges and aggregate their judgments, or anything fancier than that, you can use that, and you should probably use that in ZSV. As for the data generation part, we didn't really find a problem with, for example, you could think of that maybe Claude would have an easier time answering the instances that Claude generates. We didn't measure that. I'm willing to believe that might happen, but I'm not so sure. I'm not so sure. I'd have to check it. But with the judge, yeah, it's definitely a problem.
Any more questions?
So you're presenting a framework to evaluate the models to rank model.
Yeah.
How do you feel that in the future this will play a role in setting the quality of model evaluation.
Yeah. So we don't want to remove humans from evaluation. I think ultimately, like I said at the beginning, I mean, this is not a substitute for human evaluation. No automatic evaluation method is. Automatic evaluation is born from the need of being able to move fast and to develop faster. So you sort of accept the sacrifice of you're going to have a worse evaluation, a noisier evaluation, but it's going to be much faster. And that's more worthwhile than waiting for a human evaluation at every step of the way when you're developing a model. So this was developed a lot from the perspective, this was what we did at the team at Unbabel. It's what we do at SORT. We train models. We have a new checkpoint every other day, every week. We would love to have human evaluation every single checkpoint, but we can't. So we take these sort of local minima decisions at each point. So that's a motivation for automatic evaluation in general. I do believe, though, that we have to prepare for the case, and this kind of already happens in some tasks, where humans won't be able to do evaluation because either tasks will be too complex or at least won't be able to do evaluation by themselves. Like they'll need some sort of assistance. So I think as this technology improves and as we go into new knowledge and new tasks that we can't solve ourselves and possibly we can't even evaluate, we have to prepare for this scenario. So it's a good idea, I think, to start thinking of how we deal with these problems like self-enhancement bias. That's a big one. But yeah, that's a more philosophical matter. You can definitely have a human in the loop. That's what I also argued for. We working in mental health, we've done at this point several campaigns with human annotators. It's super necessary. There's also many tasks where you still can't really, this doesn't work yet because language models are not good enough, or we haven't found a way to make them good enough. So yeah, humans are definitely still very much needed.
Last question. Yeah.
Along the lines of the last question, do you have any thoughts?
No, sorry. No, I'm sorry.
Okay, that's it. Round of applause for that.
Thank you.
I'll see you in 2 weeks.